Alright class, so last time we talked about Lewis structure. We say if you have a covalent compound, two nonmetals together, there are no balancing of charges, there is no losing or gaining electron, there's a sharing electron. And Lewis structure was a way for us to figure out how they share electron and to draw out a Lewis structure for covalent compound. And then we also talked about the geometry. Once we draw out the Lewis structure for covalent compound, how would you figure out what's the geometry of that compound? And now what we're going to talk about today, we are going to talk about polarity. We're going to talk about polarity. Okay, now before we talk about polarity, let's talk about the background a little bit. If you remember, we said if you have a covalent compound, the covalent compound could be polar or it could be non-polar. For example, if I have HCl, okay, so H versus Cl, which one has a higher En value? Cl has a higher En value, is more electronegative. Now, what does that mean? That means the Cl is going to pull most of the electron toward itself, because if you have a higher En value, you are stronger. So Cl pulls the electron toward itself, and because it pulls the electron toward itself, it has more electron than it should. Okay, it has more electron than it should. Now, because it has more electron than it should, we give it a partial negative. Again, what does a partial mean? Again, this is a symbol for partial, because it has more electron than it should, because it's more electronegative and is pulling the electron toward itself. And because it's pulling it this way, then the hydrogen, it has a little bit less electron. It gives it a partial positive. And if you remember what we said what this means is electrons are not shared equally, and that's a polar bond. Polar bond is when the electrons are not shared equally, because Cl has more of the electron than hydrogen. Now, let's say I have Cl2, Cl attached to the Cl. Now, I have these two have the same En value. They have the same En value. They have the same strength. So what that means is the electrons are shared equally. They have the same strength. So no one is pulling the electron harder than the other atom. So electrons are shared equally. And every time electrons are shared equally, we call that a non-polar bond. Non-polar bond, they're sharing pretty evenly. So far, so good. So they don't share equally, that's polar bond. They do share equally, that's non-polar bond. All right. So that is what we talked about in the past. Now, what we're going to talk about, we're going to talk about molecules. We could also, when we have covalent compound, when we have covalent molecules, when we have covalent compounds, they could also be polar or non-polar. So don't confuse them with a bond. Covalent bond could be polar bond and non-polar bond. You know how to do that now. That's over here. Now what we're going to talk about is compounds could also be polar or non-polar. So covalent compounds, covalent molecules could also be polar and non-polar. And that is determined by geometry and bond polarity. Okay? And that's what we're going to talk about today. When you have a covalent bond, is that polar or non-polar? And that is determined by geometry and bond polarity. I'm actually going to give you guys the rule from right off the bat. And then we're going to do a lot of practice problem to make sure that you get this down. Let's say I have non-polar molecule. When do I have a non-polar molecule? You have a non-polar molecule if a molecule contains only non-polar bond. If you have nothing but non-polar bonds, you end up being a non-polar compound. Or you could have polar bonds. You could have polar bonds, but dipoles are cancelled out. And we'll talk about what that means. All right? Now, next one is, when do I have a polar molecule? You have a polar molecule when you have polar bonds and is not or. Now we have two requirements, and the dipoles should not cancel out. I'm going to go over exactly what these means. I'm going to go over exactly what this means, but I wanted to give you the rundown first. Okay. Now, let's do this. Our first example is F2. I'm going to draw F2 out. I have 2F bonded together. It's equivalent compound, two nonmetals together. All right. Now, this covalent compound, this is a covalent bond. Is this covalent bond non-polar or is this polar bond? What do you think? Hopefully, you're shouting that this is a non-polar bond. Exactly. It's a non-polar bond because these both have the same En value, so the electrons are being shared pretty equally. So this is a non-polar bond. So all I have is non-polar bond. If you only have non-polar bond, what do you end up having? You have a non-polar molecule. And what a non-polar molecule means? It means that electrons are distributed evenly. Electrons are distributed evenly. Electrons are pretty distributed evenly. And we can see it over here. Because here we have some electrons over here and we have some electrons over here. They're distributed evenly. So that's a non-polar molecule. Now, let's go our next compound. Let's go to CO2. Now, take a minute. We've done this before, but draw the Lewis structure for CO2. And I'm going to just draw it out because we've done this in the past. We've done it in the last lecture. Here is CO2. Okay? Now, let's go to the bond. Oxygen is more electronegative than carbon. So, oxygen is pulling the electrons this way. And this oxygen is also pulling the electrons the other way. So, this is a polar bond because oxygen is pulling more of the electron. This is also a polar bond because the oxygen is pulling the electrons that way. Okay. So I have two polar bonds. And again, and these are the dipole. What I'm drawing here, these are the dipole. It shows you where the electrons are going. Now, polar bond, polar bond. Is this molecule polar or non-polar? To be polar, you have polar bond. And the dipoles should not cancel out. Because if you have polar bonds and the dipoles cancel out, you end up being non-polar. Do the dipoles cancel out here? What do you think? They do cancel out. Think about it this way. Here is a carbon is over here. Oxygen is pulling the electron this way. But I have another oxygen that is pulling it the other way. And since these are the same atom, exactly the same strength. One is going this way, one is going this way. So these two can cancel each other out. The dipoles are canceled out. Now, because the dipoles are canceled out, what does that mean? That means overall is a non-polar molecule. So overall, ends up being a non-polar molecules because the dipoles are cancelled out. So electrons are distributed evenly. We have some electrons here, we have some electrons here. Okay, ready for next one? We're just going to keep doing practice problem until you guys get this down. BF3. Now, this is one that we haven't done yet. What I want you to do, I want you to draw the Lewis structure for BF3 for me. Okay, so pause me and draw the Lewis structure for BF3. And tell me the geometry for BF3. This is a good practice problem. So draw the Lewis structure for BF3 and tell me the geometry of boron trifluoride. Okay, so hopefully you paused me and you figured out the geometry. If you look at BF3, again this was on last video, how to do the Lewis structure, there are 24 valence electron, right? Boron goes in the middle, and then I have fluorine, fluorine, fluorine around it, yes? And we said that each covalent bond has 2 electrons, so 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. Okay, that means so it would be 24 minus 6. Everyone follow that? Again, I've already put down 1, 2, 3, 4, 5, 6 because each covalent bond has 2 electrons. So 24 minus 6 is 18 electrons left. What do I do with those 18 electrons? I have to make sure the surrounding atoms are happy. Is fluorine happy? No. It has 2, it needs 6 more. Is this one happy? No. It has 2, it needs 6 more because all of them want to have 8. So I put 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So now I have put down 18 electrons. I have no electrons left. Fluorine happy, fluorine happy, fluorine happy. Is boron happy? Boron is happy because remember, boron was one of the exceptions. Hydrogen is happy with 2 valence electron. Boron is happy with 6 valence electron. Those two are not greedy. They're good. So this is my Lewis structure. And I asked you guys to also look at the Vesper geometry and figure out the geometry. The geometry is trigonal planar. Trigonal planar. Because we have a center atom and the center atom has 3 bonds around it. Okay, so you know the geometry, you know the Lewis structure. Now the question is this polar or is this non-polar? Now let's think about this. Is this polar or is this non-polar? So here I have a boron, fluorine, fluorine, and fluorine. Fluorine have a higher En value than boron. You knew that. So the electrons are getting pulled towards the fluorine. Do you guys agree? Okay. Does this get cancelled out? Does this get cancelled out? So I have electrons going this way, electrons going this way, and electrons going this way. Now what does that mean? That means I have some electrons over here, I have some electrons over here, and I have some electrons over here. Now, as you can see, the vectors do cancel out and electrons are distributed evenly because every corner has a little bit of electron. Every corner has a little bit of electron. So electrons are distributed evenly. Again, you have to think about 3D, right? You have to think about 3D. So overall, this ends up being a non-polar molecule. It has polar bonds, but the polar bonds end up being cancelled out. Ends up being cancelled out. So far, so good? Okay. Now, let's do the next one. Our next one is HI. So these are the ones we did is HI. Now, HI, I have hydrogen bonded to iodine. Now, iodine has a high En value, so it's going to pull the electron toward itself. So this is a polar bond. Now, I only have one polar bond, so there is no way anything can get cancelled out, right? I only have one polar bond. Nothing can really get cancelled out. So this is end up being a polar molecule. If I have one bond, there's nothing to really cancel it out. I end up being a polar molecule. Okay, ready for next one? H2O. Pause me, draw the Lewis structure for this, tell me the geometry, and then figure out, is this polar or is this non-polar? Okay, now that you unpaused me, water has 8 valence electrons, and we said hydrogen can never go to the middle. So I'm going to put oxygen in the middle, bonded to hydrogen. Okay, so here we have the hydrogen over here. All right, so we had 8 valence electron. How many did I already put down? 1, 2, 3, 4. I've already put down 4, right? So what I end up having, I have 4 electrons left. I have 4 electrons left. Now hydrogen is happy over here as 1, 2, happy here. I have 4 left. I'm going to put it on a center atom. So I have nothing left. Is the center atom happy? The center atom is happy because it has 1, 2, 3, 4, 5, 6, 7, 8. Oxygen happy. Hydrogen has only 2. 2 is all it needs. Is happy. Nice job. And the geometry is bent. Okay. Now the question is this polar or is this non-polar? Is this polar or is this non-polar? Now oxygen is more electronegative than hydrogen. So the electrons are shifted towards the oxygen. Okay? So I have polar bonds and I have a polar bond. Now the question is, again, remember what we talked about. You could have a polar bond, but the dipoles should not cancel out in order for a molecule to be polar. Now the question is, would these dipoles cancel out or not cancel out? Now, let's think about this. So here, this is how the dipoles are going. The dipoles are all both going towards the oxygen which is on top. Now, if you look at this, that means I'm going to have more electrons on this side, and I'm going to have less electrons on the other end of the molecule. Do you agree? Because most of the electrons are going this way. So I have more electrons here. I'm going to have less electrons on this side. So as you can see, electrons are not distributed evenly. Electrons are not distributed evenly. Electrons are not distributed evenly. And when that's the case, electrons are not distributed evenly, what do you end up having? You end up having to be a polar bond. They're not evenly distributed out. It's a polar bond. It's a polar bond because these are not going to cancel each other out. There is no way this can cancel each other out. They're both going towards the oxygen. So this ends up being a polar bond. Okay. Now, I'm going to give you a couple more to do, and this is considered your take home, even though you're home right now. Here's your take home for next time, and the next video we're gonna go over this. You ready? This is your take home. I guess I need a new name for take home since you guys are hopefully home right now. CH3F CCl4 OF2. Okay. Now, what I want you guys to do for these ones, I want you to draw the geometry, draw the Lewis structure. Tell me the geometry and tell me, is it polar or is it a non-polar molecule? So do the Lewis structure, figure out the geometry, or a polar or non-polar. And I do have a I do have a shortcut for polarity, which I'll show you next time. But I want you to understand it based on this. Are the dipoles going to cancel out? Are they distributed evenly or no? And I'll show you the shortcut next time. Okay, don't forget, do this take home.